Hello everyone. So welcome again to my YouTube channel and this is another video. Now it's been a long time I'm not posting any video in this channel. There are some kind of personal engagement and some professional commitment. So I didn't get much of time to post any recurring videos. But yes, all of a sudden yesterday I thought of like there has been some kind of confusion in some of the Staad user. A lot of users are asking me like, okay, can you interpret a little bit on the cut along line feature in StaadPro finite element approach? You might be wondering that in Staad there is a feature by which you can dissect a finite element meshed plate and you can plot the forces or the stress diagram along that direction. If you're not aware of, let me first show you. Now, before I start off, just to let you know that this video is going to be a bit of like a casual video, like just like I'm interacting someone as a in person. I haven't made any kind of scripted stuff here so that I can make it very much well organized. Nothing sort of this. I'm just going in a flow just to explain you how I'm supposed to be for any live interaction. Okay, now this is a model. I have taken two different models. One is both of them are square in its geometrical shape. In one of them, the left hand side, you can see these are meshed with the squared shaped element, and on the other side, although you can see some square tiles, but you can see internally these are all having some triangular uh, geometry. Now the idea is like just to compare like okay how can we get benefited by the cut along line feature even if it is not well defined square, if it is having some irregular pattern of meshing, having different direction or the different direction of your requirement doesn't matter. It can really help you in different kinds of engineering requirement. So first of all, let's see what exactly we are talking about, like cut along line. Those who are new to STAT, just to let you know that this is a very powerful feature, very beautiful feature. You can find it somewhere here, maybe I think, yeah, in the post processing, and here you can see. Result along line. Previously, we used to call it cut along line, but it's the same thing. It's a result along the line that you have intercepted along the certain orientation of the plate. So this is the one. Now, if you have not tried it before, it's okay. Because I have seen that there are several users who are unaware of this, but believe me, this is a very powerful feature. Now let's understand uh, how it works, and also let's first discuss like why it could be very much helpful. It could be very much ideal for certain scenarios. Okay. Now before I start off, let's have some quick illustration just to understand why it is important. Now, if I take any arbitrary slab element like this, maybe. Now, if it is having a different shape, like a kind of trapezoidal shape or anything, okay? Now, if you want to mesh, what you can do, you can mesh by some structured pattern. Structured pattern means having a very well-defined division, maybe rectangular, but it is not rectangular in shape. It is having some trapezoidal or triangular shape. So whenever you are meshing it, you're not going to have a kind of pattern where you are meshing some well-defined rectangle like this. Okay, I'm just going by some free sketch. I've seen that most of the user prefer meshing like this. Why it is so? The reason being, if you go to StaadPro and if you want to design against the moment that you have obtained from StaadPro after the analysis is already performed, you could fetch the all the forces, stresses, bending moments, everything in a very well organized pattern. Why it is so? If I show you by a different color, maybe, for example, this is the one, right? If I want to show the local axis orientation of every plate elements, these are, I'm showing it by L. L means one of them would be X and other would be Y axis. So any one of what would be X or other would be Y. So these are all oriented in a very well organized directions. So these are all uh, are oriented along the proper direction, essentially along the edges of this rectangle. What is the benefit out of this? Whenever you are getting like moment against which you are going to design the reinforcement, the moment that you are going to get instead, for example, you are getting something like MLX or MLY. These are all known as the local axis moment. Okay, what is the local axis moment? Means moment computed about the local axis orientation. Now, this convention you have to know because instead, if you go, I'll show you maybe how these are to be obtained or how you want to see that in the post processing or in the graphical user interface. Now, the main challenge here is if it is well organized, then it's fine. All the local axis orientation, because these axis system that I have mentioned here, these are all local axis. Okay. Now there is also one axis called global axis. If I open StaadPro, maybe I can show you here, and this is the global axis system. Okay, but there is also local axis system. If you hit Shift letter T, T as in Tom, you can see small little individual axis systems are appearing. Now these axis system are essentially the local axis system. Now here you can see in this square pattern, you can see all the local axis system are very much well oriented, very proper direction they have. They are having some unidirection. So yeah, they are well organized. But on the other hand, if I zoom this guy, you can see these are almost like an haphazard, like some of them are oriented in other direction. Essentially, for every element, the first node is considered as the start node, and the second node is the obviously the second node itself for these edges. Now, the first axis, that is x-axis, would be oriented from the first node to the second node. So every other element would have its own individual unique local axis orientation. Okay, so the uh, pitfall here is if I going back here, so if you have a very well defined local axis system like this, you can get, okay, my all the local axis moment I'm getting. So you can understand that if I slice a line like this, you can understand that, okay, uh, if it is MLY is applicable, you can understand that these are all moment computed about this line. Okay, if you're going straight, okay, means you are if you are bending something, right? There would be some axis of bending, right? So as this line is coinciding with your local axis orientation, so there is no issue in using those values for rebar designing, right? But what if I have a situation like this, maybe I'm choosing the red color. Yeah. So if I make a very random mesh like this or maybe this. I'm just going freehand here. Okay, now if I go like this, say for example, this one having the local axis orientation like this is having like this is having like this, so on and so forth. So all the local axis movement that you are getting out of the post-processing information, as I mentioned, these are all in this local axis, reference. There's also global axis, but global axis you only have these two axes. I'll come to that later on. But if these are local axis moment that you are getting, now every other element has its own direction. That means the moment calculated for this would be about this direction. Moment calculated for this would be somewhat, if I see this is x and this is also x, about this maybe. moment calculated for this, if I consider this as x, it would be along this. So like this means all would be having a different axis of, bending, against which the local axis is moment is considered, because all the moments are calculated about the local axis system, and all the local axis orientations are very different to each other. So in a nutshell, if you want, like if I draw by the blue color like this, if you want the moment to be calculated about this one, then what you need to do, you need to resolve all those local axis moment about this drawn line. Okay, and then only you can find that, okay, about this line I'm getting this moment which is of use. Because if you want to design, because obviously you want to design your enforcement about this local axis moment. Now if you want to design about this individual moment, how your enforcement would be looking like in the real life scenario, let's say it would be somewhat like, let's keep it like this color, maybe this color. This is a reinforcement color, okay? So it would be looking like this. For this one, it would be looking somewhat like this. For this, it would be looking like this. For this, it would be looking like this. So every element would have its own orientation of design reinforcement, which is not practical. You're not going to put those reinforcement like this in your real life construction site, right? So you want to maintain some uniformity like this. So you have to resolve the moment about this required direction, and against this moment you want to calculate the reinforcement. Okay. So the idea is you have to resolve it, but there is a formula. I may post it in this one, uh, by which you can resolve local axis moment about the different directions of your choice. Even if it is a global axis, that's fine. It's very much similar to the formula that you might have come across, the wood and armor movement, okay? The direction along which you want the reinforcement to be designed. Okay. So this is a bit cumbersome because instead, if you have meshed everything and you want to calculate this, even if it is through some Excel engagement, still it is very difficult, very tedious. So we don't want this. There is a very quick and very effective way to overcome this. So here, let's go back to my model. So this one, I have purposefully taken two different type of meshing. Let's switch this off. Okay. Okay, now here you can see, like, I have this two guy. Now if I am being told, like, okay, I want to design the reinforcement about considering that my moment direction would be like this. You can see my cursor. Okay. If it would have been bent about this axis, I want to design the reinforcement against this. You can find that. Okay. All you need to do, all the local axis moment should be resolved along these directions. So let's see how this cut by line or result along line is going to help us here. So for example, this is the result along line. I've already created few of them just to, demonstrate you. For example, I am putting this guy like this, and I'm just selecting a start point and ending it, and just put select somewhere outside. You can see here, this line is like I have sliced this slab along this line. I have just cut this slab. Just virtually, you just imagine that I have sliced this slab along this line. Now, if I want to calculate the bending moment along this line, how I'm going to do that, right? As I mentioned, manually you can do all those elements. You have to calculate the local axis moment and find the angle that is formed in between those local axis orientation and this line, and you can use that formula that I've mentioned. You can find it anywhere, and you can solve it. Okay, but if you're using this result along line, program is doing this job automatically for you by following all those rules. Okay, so what it does, if you see here that it has passed through this element, then this one, and it's kept on going like this. Okay, so for every element, there is an individual local axis orientation, program would resolve it along this drawn line automatically. And here you can see the type of stress. Obviously, the moments can be interpreted as a stress and also the forces. There are a lot of different types of stress. This is very much similar to the plate stress that you can see in the post-processing file in a normal scenario. Now here you can see all the different types of stresses, secondary stresses like principal stresses, von Mises stresses, Tresca, maximum, absolute, and so on. However, these are the primary force or stress representation we are doing it here. We have implemented it because this feature was there. Cut along line was there long back, but a few of the notation and interpretation we have just tweaked around a little bit in few of the versions earlier. So this is, you can see, this is M is for moment, Q is for shear, and S is for your in-plane axial forces. So let's talk about the moment first, because this is mostly to just check like how, because most of the cases you are working with the moment, bending moment, because the slab reinforcement design, mostly we are concerned with the flexion, right? So this is a little bit, initially you might be having a little bit of confusion, but you needn't have to worry. Let me interpret with some illustration which might make the thing looks very easier. So let's see or check this guy. Okay, MT. So what is MT? MT is a fictitious line and this moment. And if I click on this, this is the number of division. You just keep a watch on this one. So if I cut the line like this and the moment that would be calculated along this line, if you view it from this direction, it would look like this bending moment diagram. Okay, so this is just a representation. So this is how it goes. Now the point is, definitely you can find the stress here. You can see these 20 division means I have just made some more finer calculation points at the intermediate locations. So maximum is 20. And also, if you go to total force, you can see all the moments. Essentially, this stress is represented as kilonewton meter per unit length. So kilonewton meter per unit meter. So all those stresses has to be again, because this is like representation is not like the total force. Every element has got its individual stress value, and these are per unit length. So you need to know that, okay, what is the total length of this individual element, multiply it, and you sum them up to find the total moment that this section is going to experience. Okay, and then you can find the total forces. Okay, so either way, you can get the stress of this individual elements along this direction, or else you can go to this total force to find this total forces here. Now, you can find here there is a mention of this ms, mt, and so on. Now, let's make it a bit shorter here so that we can come to the point. Now, I have just made this as a quick representation. So let's see it like this one is first, this one is second, and this one is third. Okay, fine. I'm just deleting this because I don't need this. Okay, maybe I can go here and delete this. I have already intersected or drawn the line along these two directions just to show you like how we can arrive to some validation like, okay, it really works. Okay, now, first of all, let's interpret this notation here. Okay, now this is very straightforward. Rather than I draw something here, it's already there explained in the help manual, but maybe I can just bring it here. Let's see if I can. Maybe I can put it here. Okay. The first time if you are using it, now this notation looks very tricky to understand, but it's not that complicated. It's very easy. Just you need to know the interpretation here. So this is the fictitious line that we have drawn, and this double arrow means the moment just determined about this line. Okay, and this is for the stress. You might have seen there are two different tables. One is for stress and one is for force. Okay, that is represented by MT, and the other orthogonal direction is represented by MTS. For now on, just follow this notation, and you can find that okay, which forces you are going to pull from that table, which are the forces of your interest. So again, there is also another table on its right that is for the force, and for the force, that means very simple, means all the individual stresses are multiplied with the respective unit length or the respective length of those individual elements, and they are added together to find the total forces. Okay, so we are converting from the stress to the force. So this in this portion, you can see if I go to this line, so the total force that we can interpret is shown as an ms here. Okay, so if I want to design the reinforcement, considering that the bending is going to happen here, then I have to take the moment along this line, right? That is the ms moment, that is for the force. And if you want to consider the individual stress, then you need to consider it as a mt. Okay, understood? Now let's quickly see like how we can validate. Now in this model, I have added unit pressure. Unit pressure means just like a load intensity. It's a pressure load of minus 10 kilonewton per meter square. Okay, on the gravity direction. I'm just looking it from the top view. Okay, now let's go back here, and I have already performed the analysis. And now this one, let's first, I have made it very simpler. Okay, I have just put a plate like this and put some fixed support, just like a cantilever kind of slab. Now we can easily find the moment at this location. This location is very close to the support, so it's very straightforward. I have already calculated this so that I can just quickly bring it here. So this is my section. Now this is my load intensity, means force per unit area. Now just consider this as a kind of cantilever, just like a cantilever beam. So that means I am just converting this unit force per unit area into force per unit length. Length means along this length. Okay, so what I can do, this area I can multiply with this total length to find that what is the load intensity per unit length rather than the per unit area. Okay, so what I need to do, this one, this is the 10 kilonewton per meter square. I can multiply with this dimension, that is 6.096. Okay, so I have already done that and it's coming out like 60.96. Now you know that to find the end moment of a cantilever beam, it's very straightforward. This is W times L square by 2. W means uh, load per unit length. So that's the reason I have just converted from per unit area to per unit length times its distance up to the support, its square, uh, divided by 2. Okay, very straightforward. So here I have taken the length from this one because I have sliced this here. It would be very much close to the support moment, but still I want to make it very much close to some expected value. So here I have taken this length of, because this is B, I have taken this one from this red mark to here. 5.715 because there is a little bit of distance to go, right? So from here to here, it is less than 6.096, but very close to that. So it's coming around 5.71. I'm just use this formula here, and my moment means this total force, I mean, about this line is 995 kilonewton meter. Now it's almost close to 1000. Okay, fine. Now let's go here and see how we can see these values from here. Now this one, let me make it more accurate by using number of calculation point higher. I'm just updating it from 2 to 20. Okay, now the one that I am selecting here, it's turning red. That means the one that I have just clicked on, that cut along line is being selected. So the first one, if you see this empty that I have already explained you, it is going to be like moment about this line. Okay, so this empty, if you see here, the value, you can see the graphical interface, graphical representation of this moment diagram. And you can find all those individual plates stress values. I'm just dragging it a little bit to just to show you. Uh, this is one. Okay, so I'm interested in empty, so it's empty is only reported for every element. Now you can see 90 means this one is 90, I think. I think this is 90. Yeah, 90. You can see so many 90s are there because within 90 I have several internal divisions because I have updated the division from 2 to 20. Okay, so you can calculate from the stress. You have to just multiply each of those values with those individual length and find the total value. But Staad is also there to calculate the total moment out of this. So you needn't have to do this exercise. Rather than that, Staad has already performed this calculation. So here you can see from P90 to 7474 is this, I think. So you can see here my total moment calculated is uh, this one. As I mentioned, this is a little bit initially it is very confusing. This empty line, if I show you again, just for your reference, uh, this empty represents stress and this ms represents total moment, okay, total force, okay. So right now we are interested in total force. So we have initiated the stress calculation from here, and from the stress the total force is computed. So here you can see in the ms line, which is our line of interest or the force of interest, you can see the value is around 1011.2 kilonewton meters. So it is very close to the value that we have calculated. Okay, very close to. There would be a little bit of a difference. Finer you do the meshing, the closer would be the value. Okay, so this is the first one. Second is this one. That is the most important thing because this one you can easily calculate from the normal post-processing result also, right? Because these are all oriented along the well-defined direction. But what about this? Every local axis has its own unique orientation for every triangle the line has intercepted through. But as I mentioned, all those local axis moments are eventually resolved along this line. So the total force is calculated along this line after the forces after all those stress are resolved along this line and they are converted into the total forces. So here also, if I select this guy, it is coming along 1008.165. So you can see the values are very close to each other. We have already checked that with some hand calculation, it's also matching. So why I have shown this? Because uh, you might not be lucky enough to get every time a well-defined rectangle. For this has been a common question to us that if I want to do the polygonal meshing like triangular meshing, how to use those local axis moment for slab design. Now, one thing is like you can take the local axis movement, convert them manually to the required direction, and add them together to find the total movement along the line of your interest. That is one way, but that's a tedious process. You have to do all those manual operation. But here you can get the total moment along the line of your interest. Now, if it is having a trapezoidal shape like this, say for example, this one, let me make it a little bit more irregular like this, for example, like this. Now, this is like a slab and you want to, okay, consider the slab design so that the reinforcement, if I show by green color reinforcement, you want to lay along these directions, okay? It has to be uniform, right? Means uniform means it has to maintain some proper orientation. Okay. Now, if you are, first of all, you can't have a well-defined rectangular meshing with every element would be generated as a square or a rectangle. You can't do that. Even if you're doing quadrilateral meshing, the meshed element would be less somewhat like this. So you can either use the quadrilateral meshing or the triangular meshing, it's up to you, but all the local axes that would be formed for each and every element would be very unique. So what you need to do, you need to draw a line like this and find that, okay, what would be the total moment about this line and use the respective moment for calculating the reinforcement needed to tackle that forces. Now, there are two different approaches. You can take total forces or you can split them into different zones and you can use the forces for that particular zone. For example, for this zone, you can three zones we have subdivided just for a reference here. You have taken from here to here one zone where you have calculated the total forces. From here to here, you have calculated another total forces from here to here and the total forces. So what you need to do, you need to draw a line from here to here, one line, you are getting total forces. Another, in another step, next step, you can draw another line from here to here and just put the direction along which you want to calculate, and you can find the total forces in the in this table that I have just shown you. Like this, you can easily find the total reinforcement required to resist that moment about any direction of your choice, and you can lay the reinforcement exactly along these directions. So this is the beauty of the result along line. If you have any question or queries, please drop your questions, drop your concerns in the comment section. Maybe if I come across them, I'll try my best to explain this. And this is a really very powerful feature. So you might have seen that I have gone a very casual way of explaining this. I have not made it a kind of scripted video. Just whatever I know, I've just explained it. But this is really a very powerful and very effective tool. Many users know this, many users might not know this, but even if they know, they might not know the actual utility of this. So this is one scenario where you can apply this feature for your real life design exercise. Okay, so signing off. See you in the next video.